Our goal today is going to be to design an entirely new representation for sets and maps. So let's reflect on what we've done so far. In the last 3 lectures, we spent a lot of time talking about these search tree-based approaches to implementing sets and maps. We saw the binary search tree first. Pretty easy to implement, but the bad news is that the worst case runtimes for our contains and add operations, if we're talking about a set, are theta n. Now we do have the caveat that randomly generated trees are theta log n, but it's not safe to assume our trees are random. So we came up with the idea of the 2-3 tree. Those were cool. They're beautiful. Real nice, simple idea, and they gave us this runtime that was theta log n, but they're hard to implement. So we kind of just passed on trying, and instead came up with a new idea, which was the left-leaning red-black tree, which is still hard to implement, but much easier than the 2-3 tree. And the basic idea is it maintains a bijection or a 1-to-1 mapping with 2-3 trees, and we get that nice theta log n time. Great. All right. So now that we've achieved all that, there's some questions we might ask ourselves. So the first observation I'm going to make to raise one of these questions is that our search tree sets required our items to be comparable. So we need to be able to ask, for example, is x less than y to step through a tree? And that's not true of all types out there. Some types do not, in Java, for example, implement the comparable interface. So could we somehow avoid the need for objects to be comparable? Is that possible? Can we still do rapid finding when we can't do comparison? Another is that our search tree sets have excellent performance, but it would be nice if maybe we could do better. So I should note that theta log n is really good. It is amazing, like magnificent. If we have 1 billion items, the tree is still only going to be around height 30 due to the magic of the log function. But maybe you want to do better than log n. So in this lecture, we're going to be developing a way that we can indeed do better than log n, and we can avoid the need for objects to be compared. And it's a very interesting and important idea that we'll ultimately learn is called a hash table. But we're going to start small. And we're going to start with this strange idea, which I'm going to call a data indexed integer set, which is just something I made up. Okay? This is not something you could Google and find. So the idea is, let's just create an array of booleans that's indexed by our data. Okay? And initially, all of our values will be false. Now when we add an item, we're going to set the appropriate index to true. So when we create a data indexed integer set, it's basically a gigantic array of tons and tons of false values. This is basically a set containing nothing. But then if I say add 0, what will happen is that the 0if item in my Boolean array will be set to true. If I then say, okay, well, let's add 5, then the 5th element will become true. If we go to, say, let's add 10, then we go to the 10th item in my array, and I set it to true, and maybe I do 11. Okay? So it's actually a pretty intuitive idea. And at its heart, we're just creating a gigantic array and then accessing the appropriate element corresponding to the data. And with integers, that's very clear. If I want to go find the element in the array corresponding to 5, I just go to position 5. Okay? So this is the integer version of something that we're going to generalize soon. So this is a really simple idea that relies on the fact that accessing an element of an array is constant time, no matter what element you're looking at. That's just a feature of real computers. Now what's nice about this is that the implementation is about as simple as you can imagine. You create a Boolean array, say of size 2 billion. Then whenever you call insert or add, I really should have called this add for consistency, sorry about that. I changed this semester and forgot to update the slide. But anyway, if you add an integer, you just set the ith element of the present array to true. And whenever you do contains, well, you return the ith element of the present array. That's it. This is the whole implementation. And so the runtime for this thing is simply going to be constant time for both contains and add. And what's nice is you'll notice there's no actual comparisons happening at any point. So this is kind of a silly proof of concept that we can get better performance and avoid the need for any comparisons and end up getting a much simpler implementation. Now there's some very obvious problems with this approach. One is that it's extremely wasteful of memory. So if we want to check the presence of all positive integers, we need 2 billion booleans. So we're just wasting enormous amounts of space to store a bunch of false values. And another problem, of course, is that we need some way to generalize beyond integers. But this lecture is basically going to be all about addressing these concerns, and ultimately, at its heart, this is what a hash table is going to be all about, exploiting the constant access time needed to find an element in an array. Okay, so let's see how we can fix these problems in the coming videos.